Okay, great. Awesome. So I wrote some code to actually look at the first. So this is not supposed to be a proof, in other words. By looking at these first few numbers, it's not supposed to tell you anything. Just to give you a picture of what's happening. And the general argument is that when you expand things, the expressions are going to tend to be bigger. And you want to benefit from keeping numbers in a factored form. So we're going to look at the first 13,000 numbers, and you get to pick which number you want to look at in both encodings. All right, so Phil, what number would you like to look at in the range 2 to 13,000?
123,456.
So 123,400 and what? 56? So since the index starts at 0, I have to write this. So this expression is the factored encoding. If we look at the, so you don't have to trust me. This is what it looks like when you write it in the Goodsteing encoding. All right, so here you see it doesn't seem much bigger. You save a bit of space, but it doesn't seem like a big deal. All right, so Simao, what number do you want to check?
20, does it have to be big?
No, no. You pick any number you want in the range.
25,097.
35,097? Oh, 25, sorry. So 96.
97 is right.
Yes, but the index starts at 0.
Oh, okay.
So it's a list, it starts at 0. So if I want to give you a number, I just give you this. So this is what it looks like in the factored format. And this is what it's going to look like, 25096. This is what it looks like in the Goodsteing encoding. All right? So I can't see the general pattern here. Let's actually look at a curve of what's happening. So here's what happens. In green, what you're looking at is the encoding in base 2 in the factored encoding. So this is just the length of the string when you write things in the second canonical form. This is the length of the string when you write things in the first canonical form. So why does it do this zigzag, and why does it eventually go down? Well, it goes down when you hit a power of 2. So when you hit a power of 2, no luck, the two encoding have essentially the same length. So the argument here is that expected, this pattern is not going to suddenly change. So as you go on, it's not going to be the case that all of a sudden this is going to go below and this one is going to go above. So it's not a proof because we're not going that far. However, the argument is this pattern stays. And you are winning expected length. The expected length is shorter for these strings. All right? So I'm not claiming a proof. But this is an experimental empirical observation that I made, and I'm working toward giving a systematic proof that if you count the expected length of your string in the second canonical form, you're actually winning in space. Now there's some drawbacks. The drawback was integer arithmetic becomes as hard as factoring. However, if you want to find the second encoding, you shouldn't factor. There's a way of actually finding the second encoding without factoring, and essentially equates to sieves. So the way I computed this was not to go and factor every number, because that takes a while. You essentially sift the numbers, and this is exactly a follow-up on the talk I gave last year. You sift the numbers and keep track of the symbols every time you recover a new prime. You just add 1 to your string. All right, so I think, let me see how much time I have. All right, good. So I'm ready for the open problem. And I can tell you why was Goodsteing interested in this. So Goodsteing is a logician. Good, I can turn this off. So Goodsteing was a logician, and he pointed out this encoding in respect to a fascinating problem. And the corresponding problem in the prime encoding is much harder to solve. So Goodsteing said, let's take our number, 7. Actually, 35 was better. Let me just write it. Let me turn on the light. it. So take the following number. All right, so you remember that when I write x, I really mean 2. Right, so let me write 2. 2, 2, 2, 2. So Goodsteing said, start with a number encoded this way, and then change the basis into the next integer. So the base is going to increase. So the sequence says, turn this number into 3, 3, 3 plus 1. So this is in the power, plus 3 plus 1. All right? And he says, subtract 1 to it. If you subtract 1, you get a new number that you can encode in base 3, recursively in base 3. All right? So this number is going to be 3 to the power 3, 3 plus 1, plus 3. This is your number. This is the number we get. So we started here. We substituted the basis by the next integer, subtracted 1 to it, and returned this new integer. So Goodsteing says, do the same things. Change the basis by 4 now. So this number is going to be, on this side of the board, it's going to be 4 to the power 4, 4 plus 1, plus 4, and he says subtract 1 to it. Okay? And then go to the next integer. This sequence grows extremely fast. Goodsteing was able to show that it eventually goes to 0.
No.
Yes, it's extremely surprising. He says the sequence eventually goes down to 0. The proof is highly non-trivial, and that was the goal of his paper in 1944. All right, so now I showed you a different encoding.
Did you show an example? What does eventually mean in this case?
So the length of the sequence is very long, and the proof needed ordinals. I mean, the proof, I'm not going to get into it. I can give you the reference to the paper. You should definitely
No,
look
I'm
it up.
not interested in the proof. I just want to see just one.
One sequence. So actually, there's a website that you can see the sequence being generated, and I don't think you have any luck in seeing this, the length of the sequence be less than 1 billion or so. I mean, for the small numbers, I don't think you have, if you wait your lifetime, I think you get to see it go to 0. The proof is actually, I'm not going to go into the proof.
I think maybe cheating because it's very, eventually maybe in a logician's meaning.
Yes.
Eventually it will happen.
Yes, well, I give you that.
Yeah.
Okay, but the argument here is,
Do you have a specific example, but eventually less than 10,000?
no, I don't. I don't have a specific example. However, we can argue, formulate a similar problem in the prime recursive encoding. Okay? All right. So here, you see, he has the luxury of iterating to every number, because you can write a number in any basis. However, in my prime encoding, I'm stuck with the primes. Okay? So here's how the question is formulated in the prime encoding setting, and I don't know how to prove this. I don't even know whether it's true that the sequence will go to 0. So pk, and this is product of pk's, pt's, so product over the k, and so on. All right, so this is a recursive prime encoding. So what do I do? Substitute every prime by the next prime. Right, so every prime is going to be substituted by the next prime, and subtract 1 to it. Okay? And then you continue doing this. The question is this going to go to 0? Okay, so Goodsteing did not answer this question in his paper, unfortunately. But this is an analog question for which I'm trying to find out whether I can tweak his proof to prove this. And right now, it's an open question. And with this, I end my talk.
Thank you very much. Time for questions.
I have a question.
Yes.
Do you have an idea what the complexity is of, if I give you a number in the, what's his name, Goodman's?
Yeah, Goodsteing
And
encoding,
I
yes.
say, hey, give me the prime encoding,
Oh.
how hard is it, or vice versa?
Right. So going from the second canonical form to the first one is easy. It's just expanding out the expressions.
Okay.
Going from the first canonical to the second is as hard as factoring. So you hit the factoring barrier very quickly. And the argument is you pay for the space that you saved. So you save a whole lot of space by writing things in their factored format, and you had to pay some effort to do it. You can benefit from it if you had a sequence database, but if you wanted to do arithmetics, forget it. I mean, it seems way too costly to be doing factoring every time you want to add integers. So both multiplication and addition reduce to addition. Yes?
Suppose we have a quantum computer to do our factoring.
Oh, then you're in business. If you have a quantum computer, this is how you want to encode your numbers. Absolutely. So I vouch for the quantum computer. If you have the quantum computer, you don't even need the first encoding. You will want to do this. But the take-home message is, it turns out you can do even better than this. So what's happening is, what is multiplication? Multiplication is a repeated addition. What is exponentiation? Exponentiation is repeated multiplications. So you might hit strings for which you're doing a whole lot of exponentiation, and it makes sense to introduce a new operator, which you would call the super exponentiation, and you would describe how many times you need to do this in terms of prime numbers. So the scheme continues going on. If your string becomes too long because you're repeating too many exponentiation, you can call the super exponentiation operator, and then you say how many prime number times did you have to do that operator, and recurse the same way. So if you continue doing this, you have a scheme for making your string smaller, but it becomes even harder to do additions. I mean, addition becomes the nightmare. Multiplication is even easier than addition. Right, so that's the take-home message. So you can beat the decimal system, but you pay a huge price when you want to do arithmetics. Yes?
The chart that you had comparing like the storage size for
Yes.
methods.
Yes.
Do you know experimentally like how fast the two grow?
Oh, so what is it? What is the red track? What is the red curve keeping track of? It's keeping track of the number of terms you're adding. So if you were looking at encoding numbers in base 10, it's keeping track of the size of the bits, the number of bits. So it's growing like log n.
Okay.
Right. So I mean, I would be excited to show that the green curve grows at log n, but I don't know that's true.
Okay.
But that's the hope. Right.
Do you believe in your conjecture, even in the sense of
That this should go to 0.
Yeah.
Well, no, I have no beliefs. So this is not even yet a conjecture. I have to understand the proof that Goodstein made in order to understand whether this has any hope of going to 0. But my guess is, it would not go to 0. Primes are very rare, so you're jumping very far, but I don't know yet.